The Milky Way has a secret boundary, not made of walls or barriers, but something far more absolute. Crossing it would require something most people haven't even considered. So how long would it really take us to leave? If you want to dive deeper into the universe's most impossible questions, make sure to subscribe and give this video a like. Now let's begin. The Milky Way isn't just our address in the universe, it's our cosmic prison, in a sense. Not because it holds us with malice, but because its gravitational embrace is so powerful, so all-encompassing, that breaking free demands velocities and timescales that dwarf our current technological capabilities. To understand just how long it would take us to leave this galaxy, we first need to confront a fundamental question. Where exactly does the Milky Way end? When you gaze up at that misty band of light stretching across a dark sky, you're seeing the luminous disk of our galaxy from the inside. This disk, a magnificent spiral structure filled with hundreds of billions of stars, measures approximately 100,000 light-years from edge to edge. That's the distance light itself, traveling at 670 million miles per hour, would cover in 100,000 years. Already, we're dealing with numbers that feel almost absurd to the human mind. But here's the twist that changes everything. That visible disk, as vast as it is, represents only a fraction of the galaxy's true extent. Beyond the stars, beyond the gas and dust clouds where new suns are born, there exists an enormous, invisible halo. This is the dark matter halo, a mysterious spherical shroud that contains most of the Milky Way's total mass. We cannot see it with our eyes or telescopes because dark matter doesn't emit light. We know it's there only through its gravitational effects on everything we can observe. Recent observations from missions like the Gaia Space Telescope, which has been mapping the positions and motions of over 1 billion stars with unprecedented precision, have helped scientists refine their estimates of this dark matter halo. The latest findings suggest something extraordinary. The Milky Way's gravitational influence extends outward to a staggering distance of roughly 1 million light-years from the galactic center. Some studies push this boundary even further, suggesting the halo could stretch to nearly 2 million light-years in diameter. To truly escape the galaxy, to break free from its gravitational grip and drift into intergalactic space, a spacecraft would need to travel at least 500,000 light-years from our solar system. Let that sink in for a moment. Not 500,000 miles, not 500,000 kilometers, 500,000 light-years. This is the distance that defines our prison walls. Now let's bring this down to Earth, or rather, to the fastest objects humanity has ever built. The title of humanity's speediest ambassador to the cosmos belongs to NASA's Parker Solar Probe. Launched on August 12, 2018, this remarkable spacecraft was designed to dive repeatedly into the Sun's outer atmosphere, collecting data from an environment where temperatures soar to millions of degrees. To accomplish this death-defying mission, Parker needed to move fast, really fast. On December 24, 2024, during its closest approach to our star, the Parker Solar Probe screamed through space at a record-shattering 430,000 miles per hour. That's roughly 192 kilometers per second. At this velocity, you could fly from New York to Tokyo in less than a minute. You could circle the entire Earth in about 3.5 minutes. It's so fast that it defies our everyday intuition about motion and speed. And if you're thinking this is encouraging news for our hypothetical journey to leave the galaxy, I need you to pause and consider this sobering reality. Even at this incredible speed, the fastest velocity ever achieved by a human-made object, it would take the Parker Solar Probe approximately 6,800,000,000 years to reach the edge of the Milky Way's gravitational influence. 6,800,000,000 years. To put that in perspective, that's longer than the entire age of our planet. Earth formed about 4.5 billion years ago. The first multicellular life didn't appear until roughly 600 million years ago. Dinosaurs walked the Earth starting about 230 million years ago and went extinct 66 million years ago. Modern humans have existed for only about 300,000 years. The Parker Solar Probe's speed, as remarkable as it is, was achieved using a technique called gravitational assist. The spacecraft didn't just launch straight toward the Sun. Instead, it repeatedly flew close to Venus, using the planet's gravity to alter its trajectory and velocity. Each flyby changed Parker's path, gradually tightening its orbit around our star and accelerating it to those record speeds. This is the same technique that allowed the Voyager spacecraft to explore the outer solar system in the 1970s and 80s. Speaking of Voyager, let's talk about humanity's most distant emissaries. Voyager 1 and Voyager 2, identical twin spacecraft launched in 1977, are currently the farthest human-made objects from Earth. As of March 2026, Voyager 1 is approximately 15.95 billion miles from home, traveling through interstellar space at about 38,000 miles per hour, or roughly 17 kilometers per second. Voyager 1 achieved a monumental milestone back in 2012 when it became the first human-made object to cross the heliopause, the boundary where the Sun's solar wind gives way to the interstellar medium. In November 2026, it will reach another historic marker, 1 light day from Earth. At that distance, a radio signal traveling at the speed of light will take 24 hours to reach the spacecraft, and another 24 hours for any response to travel back. Imagine sending a command on Monday morning and receiving Voyager's reply on Wednesday morning. That's the reality of deep space communication. But even Voyager 1, despite its nearly 50-year head start and its current position in interstellar space, is moving at less than 1/10,000th the speed of light. At its current velocity of 17 kilometers per second, Voyager 1 would require approximately 18 billion years to travel 500,000 light-years and escape the Milky Way's gravitational influence. That's longer than the current age of the universe itself, which astronomers estimate to be 13.8 billion years. Let me pause here to let that reality settle. Our fastest spacecraft, the ones that have traveled farther than anything else we've ever built, moving continuously for nearly half a century without stopping, would still need more than the entire lifetime of the cosmos so far just to reach the edge of our galaxy. This isn't science fiction pessimism. This is the mathematical reality of the universe we inhabit. The numbers are so extreme that they challenge our ability to even conceptualize them. When we talk about billions of years, we're discussing timescales where stars are born, live their entire lives, and die. Where entire planetary systems form and potentially host the rise and fall of civilizations. Where galaxies collide and merge into new structures. The journey to leave the Milky Way isn't just long by human standards. It's long by cosmic standards. Now you might be wondering, what if we could build something faster? What if we pushed the boundaries of propulsion technology beyond what we've achieved with chemical rockets and gravitational assists? This is where the conversation gets really interesting because it forces us to confront the absolute speed limit of the universe, the speed of light. Light travels at approximately 186,000 miles per second, or about 300,000 kilometers per second. Nothing with mass can reach this speed, according to Einstein's theory of special relativity, which has been confirmed by countless experiments over the past century. As objects with mass approach light speed, they require exponentially more energy to accelerate further. The closer you get to light speed, the more the universe itself seems to conspire against you, increasing your mass and slowing your internal clock relative to outside observers. But let's engage in a thought experiment. Suppose we somehow developed a spacecraft capable of traveling at 99% the speed of light. This is purely hypothetical, mind you. We have no technology remotely close to achieving this, and the energy requirements would be astronomical. But let's imagine it anyway. At 99% light speed, the 500,000 light-year journey to escape the Milky Way would take approximately 505,000 years of external time. 505,000 years. That's still an incomprehensibly long duration. When we look back 500,000 years into Earth's past, we find ourselves in the Middle Pleistocene epoch. Homo sapiens didn't yet exist. Our ancestors were archaic hominins like Homo heidelbergensis. The entire recorded history of human civilization, from the first cities in Mesopotamia to the present day, spans less than 6,000 years. We're talking about a journey nearly 100 times longer than all of recorded human history. And here's something that really drives home the cosmic scale we're dealing with. Even traveling at the speed of light itself, which is physically impossible for any object with mass, the journey would still take 500,000 years, 500,000 years of continuous travel at the universe's ultimate speed limit. There's no shortcut around this. The distances involved are simply that vast. This reality actually connects to something I explored in another video about why no civilization could ever spread across the galaxy. The sheer distances combined with the hard limits imposed by physics create barriers that technology alone might never overcome. If you haven't watched that video yet, I highly recommend checking it out after this one. It explores the Fermi paradox and the practical limitations that might keep advanced civilizations confined to their home systems, even if they develop interstellar travel capabilities. The link is in the description and on the card above. The challenge isn't just distance, though, it's also the nature of space itself. When we imagine interstellar or intergalactic travel, we often picture empty voids, but space is never truly empty. Even in the vast gulfs between stars, there exists a thin interstellar medium composed of hydrogen atoms, dust particles, cosmic rays, and various forms of radiation. At conventional speeds, this poses minimal risk, but at relativistic velocities approaching the speed of light, even individual hydrogen atoms become hazardous projectiles. Imagine driving through a light rain at highway speeds. Now imagine driving through that same rain at 99% the speed of light. Each raindrop becomes a devastating impact, carrying kinetic energy comparable to a bullet or worse. The same principle applies to the interstellar medium. At extreme velocities, the very fabric of space becomes hostile, requiring shielding technology we can barely conceptualize. Recent research from particle physics experiments, including work done at facilities like CERN, has helped us understand the energies involved in high-speed collisions. When particles collide at near-light speeds in accelerators, they produce temperatures and pressures that briefly recreate conditions from the first microseconds after the Big Bang. A spacecraft traveling at such velocities through the interstellar medium would face similar bombardment continuously for hundreds of thousands of years. This brings us to another critical consideration: time dilation. Einstein's special relativity predicts that time passes differently for objects moving at different velocities. This isn't science fiction speculation, it's confirmed fact, demonstrated by precise atomic clocks on GPS satellites, which must account for relativistic effects to maintain accuracy. For a spacecraft traveling at 99% light speed, time aboard the vessel would pass more slowly compared to observers on Earth. The mathematical relationship is governed by the Lorentz factor. At 99% light speed, time aboard the spacecraft would pass at roughly 1/7 the rate experienced by someone stationary relative to the galaxy. This creates a bizarre scenario where the journey that takes 505,000 years from our perspective might only feel like 72,000 years to any hypothetical travelers aboard. Still an impossibly long time by human standards, but significantly different. If we pushed even closer to light speed, say 99.99995%, as mentioned in scientific literature about travel, to the galactic center, the time dilation effects become even more extreme. At such velocities, decades could pass aboard the ship, while millennia elapse outside. But here's the existential challenge. Even with time dilation, you're still aging. You still need life support, energy, protection from radiation, and anyone you left behind, any civilization that launched you, would be long gone by the time you reached your destination. The European Space Agency's Gaia mission, which I mentioned earlier, has revolutionized our understanding of the Milky Way's structure. Launched in 2013, Gaia has created the most detailed three-dimensional map of our galaxy ever produced, tracking the positions, distances, and motions of over 1.8 billion stars. This data has revealed that the galaxy is far more dynamic and complex than we previously imagined. The Gaia data shows us that stars aren't just sitting still in space. They're moving in intricate patterns, orbiting the galactic center along complex paths influenced by the distribution of visible and dark matter. Some stars move in orderly circular orbits within the galactic disk. Others follow highly elliptical trajectories that take them plunging through the disk and out into the halo before falling back again. The galaxy is a churning, dynamic system, and understanding these motions is crucial for any hypothetical journey beyond its boundaries. One of Gaia's most fascinating discoveries involves stellar streams, long trails of stars that were once part of smaller galaxies, or star clusters that the Milky Way has gravitationally disrupted and absorbed. These streams stretch across hundreds of thousands of light-years, visual evidence of our galaxy's cannibalistic nature. Over billions of years, the Milky Way has grown by consuming smaller neighbors, and it will continue to do so. In fact, we're currently in the process of absorbing several dwarf galaxies, including the Sagittarius Dwarf Elliptical Galaxy. This galactic cannibalism raises an interesting point about what it means to leave the Milky Way. The boundary isn't a sharp edge, like stepping through a doorway. It's a gradual transition where the gravitational influence of our galaxy slowly diminishes, and the gravitational pull of other structures like the Andromeda Galaxy or the broader local group of galaxies becomes more significant. Space doesn't have border checkpoints. The transition from inside to outside the galaxy is fuzzy and depends on how you define the terms. Let's consider our cosmic neighborhood for a moment. The Milky Way isn't alone in the universe. It's part of what astronomers call the local group, a collection of more than 80 galaxies bound together by gravity. The two dominant members are the Milky Way and the Andromeda Galaxy, also known as Messier 31. Andromeda is the nearest major galaxy to us, located approximately 2.5 million light-years away. Now, 2.5 million light-years might sound impossibly distant, and it absolutely is by any human measure. But in cosmic terms, Andromeda is practically our next-door neighbor. The space between galaxies within the local group is relatively small compared to the vast voids that separate galaxy clusters. And here's something remarkable. Andromeda and the Milky Way are on a collision course. They're moving toward each other at about 250,000 miles per hour, and in approximately 4.5 billion years, they will begin to merge. This future collision won't be catastrophic for individual star systems. Space is so vast that even during a galactic merger, the chances of actual stellar collisions are incredibly small. Stars will pass by each other like ships in a very, very large night. But the gravitational interactions will dramatically reshape both galaxies, likely producing a giant elliptical galaxy that astronomers have already nicknamed Milky. By the time this happens, our Sun will be nearing the end of its life, having expanded into a red giant that will likely engulf the inner planets. But I'm getting ahead of myself. Let's return to our central question. How long would it actually take us to leave the Milky Way? We've established that with current technology, we're looking at timescales measured in billions of years. So what would it take to make this journey feasible, or at least comprehensible, within time frames that might matter to a civilization? The answer requires us to completely reimagine propulsion. Chemical rockets, which have powered every spacecraft humanity has ever launched, are fundamentally limited. They work by expelling mass in one direction to create thrust in the opposite direction, according to Newton's third law. But they must carry their fuel with them, and fuel has mass, which requires more fuel to accelerate, which adds more mass, creating a vicious cycle known as the tyranny of the rocket equation. The rocket equation, first formulated by the Russian scientist Konstantin Tsiolkovsky in the late 19th century, describes the mathematical relationship between rocket velocity, exhaust velocity, and the ratio of initial mass to final mass. It reveals a harsh truth: achieving high velocities requires exponentially increasing amounts of fuel. To reach even a small fraction of light speed using conventional chemical propulsion would require fuel masses larger than planets. It's simply not practical. This is why scientists and engineers have explored alternative propulsion concepts. One of the most promising is the ion drive, which uses electricity to accelerate ions to very high exhaust velocities. NASA's Dawn mission, which explored the asteroids Vesta and Ceres between 2011 and 2018, successfully demonstrated ion propulsion for deep space exploration. Ion drives are far more efficient than chemical rockets, but they produce very low thrust. They're excellent for long-duration missions within the solar system, but still insufficient for interstellar speeds. Another concept that's gained serious scientific attention is nuclear propulsion. This comes in several varieties. Nuclear thermal rockets use a nuclear reactor to heat propellant to extreme temperatures before expelling it, achieving higher exhaust velocities than chemical reactions. Nuclear electric propulsion uses a reactor to generate electricity, which then powers ion drives or similar systems. And then there's nuclear pulse propulsion, a wild concept from the 1950s called Project Orion. Project Orion, developed by physicists including Freeman Dyson, proposed using nuclear explosions to propel a spacecraft. The idea was to detonate nuclear bombs behind a heavily armored pusher plate, using the blast to drive the vehicle forward. It sounds insane, and in many ways it is, but the physics actually works. Computer simulations suggested that such a system could theoretically achieve velocities of up to 5% the speed of light. At that speed, the journey to escape the Milky Way would still take 10 million years, but that's at least getting into timescales where we might imagine multi-generational solutions. Of course, Project Orion was never built. The Partial Nuclear Test Ban Treaty of 1963 prohibited nuclear explosions in space, among other environments. And there are obvious concerns about radiation, reliability, and the sheer audacity of the concept. But it demonstrates that reaching meaningful fractions of light speed isn't purely fantasy. It requires enormous energy and radical engineering, but the laws of physics don't absolutely forbid it. More recently, scientists have explored concepts like fusion propulsion. Nuclear fusion, the process that powers the sun and stars, releases far more energy per unit mass than nuclear fission. If we could develop compact fusion reactors suitable for spacecraft, and that's an enormous if, given that we're still struggling to achieve controlled fusion on Earth, despite decades of research, we might reach velocities of 10 to 15% light speed. At 15% light speed, the journey to leave the Milky Way drops to approximately 3.3 million years. 3.3 million years is still absurdly long. To provide context, 3 million years ago our ancestors were early Australopithecines, small-brained hominins just beginning to use primitive stone tools. The entire genus Homo, to which modern humans belong, has existed for less than 3 million years. We're talking about timescales that dwarf not just individual human lifetimes, but the entire evolutionary history of our species. This brings us to one of the most speculative but scientifically discussed propulsion concepts: antimatter. When matter and antimatter meet, they annihilate each other, converting 100% of their mass into energy according to Einstein's famous equation, E equals mc squared. This is the most efficient energy conversion process theoretically possible. A spacecraft using a matter-antimatter reaction drive could, in principle, approach significant fractions of light speed, perhaps even 70 to 80%. If you're finding this exploration of cosmic scales as fascinating as I do, please make sure to subscribe to this channel and give it a thumbs up. These videos take tremendous research and effort to create, and your support helps me continue bringing you accurate or inspiring science content. The challenges with antimatter propulsion are monumental. First, antimatter doesn't exist naturally in any significant quantity in our corner of the universe. It must be manufactured one particle at a time, using particle accelerators like those at CERN. Currently, we've produced only tiny amounts measured in nanograms, and it's staggeringly expensive. Estimates suggest that producing just 1 gram of antimatter would cost approximately $62.5 trillion with current technology. Second, storing antimatter is extraordinarily difficult. Since it annihilates on contact with normal matter, it must be contained using electromagnetic fields in a perfect vacuum. Any failure of the containment system would result in instant catastrophic annihilation. Despite these challenges, research continues. NASA's Institute for Advanced Concepts and other organizations have funded preliminary studies of antimatter propulsion, recognizing that if the obstacles could be overcome, it represents one of the few pathways to truly high-speed interstellar travel. But even antimatter propulsion, as remarkable as it sounds, doesn't fundamentally solve the problem of leaving the Milky Way. At 80% light speed, a velocity that would require technological breakthroughs we can barely imagine, the journey would still take approximately 625,000 years. We're still talking about timescales that exceed all of human civilization many times over. This is where we need to confront a deeper question. Perhaps the issue isn't just technology. Perhaps the problem is biological. Human beings weren't designed for journeys lasting hundreds of thousands or millions of years. Our lifespans are measured in decades, not millennia. Even if we could build a spacecraft fast enough to make the journey in, say, 10,000 years, which would require velocities approaching 98% light speed, no human crew could survive that long. This limitation has led scientists to consider several possibilities. The first is the generation ship concept. Imagine a massive vessel, essentially a self-contained world, large enough to support a complete ecosystem and a breeding population of humans. The original crew would live out their lives aboard the ship, as would their children and their children's children for hundreds or thousands of generations. The descendants who finally arrived at the destination would be so far removed from Earth that they would have no direct connection to the world that launched their ancestors. The engineering challenges of a generation ship are staggering. You would need to create a completely closed ecological system capable of recycling air, water, and nutrients indefinitely without any external input. Current efforts like Biosphere 2, a research facility in Arizona that attempted to create a sealed ecological system in the 1990s, have demonstrated how difficult this is. The project encountered numerous problems, including oxygen depletion and species extinction, despite being on Earth with emergency backup systems available. You would also need to maintain genetic diversity in the human population to avoid inbreeding over countless generations. Population geneticists have calculated that a minimum viable population would be somewhere between 500 and several thousand individuals, depending on various factors. That's a lot of people to support for millennia. The ship would need to be enormous, with robust systems for food production, waste management, radiation shielding, and artificial gravity to prevent the bone loss and muscle atrophy associated with long-duration weightlessness. Then there are the social and psychological challenges. How do you maintain social cohesion and cultural continuity across hundreds of generations? How do you prevent the development of factions, conflicts, or the breakdown of the mission purpose? People born on the ship, who have never known Earth and will never see the destination, might question why they should continue a journey they didn't choose. These aren't just philosophical questions. They're practical concerns that could determine mission success or failure. Some science fiction has explored these themes brilliantly. Arthur C. Clarke's Rendezvous with Rama and Kim Stanley Robinson's Aurora both examine the realities of generation ships. Robinson's novel in particular presents a sobering look at how such missions might fail due to ecological collapse or social disintegration. These stories aren't just entertainment, they're thought experiments that help us understand the profound challenges involved. Another possibility is suspended animation or cryogenic preservation. If we could safely freeze human bodies or significantly slow biological processes, crews could sleep through the vast journey and awaken upon arrival. This is a staple of science fiction, appearing in everything from Alien to Interstellar to Passengers. But the reality is far from simple. Current cryopreservation techniques can preserve small biological samples like sperm, eggs, or embryos with reasonable success. We can even preserve small organisms like nematode worms, but preserving and reviving a complete human body with its trillions of cells and intricate systems remains beyond our capabilities. The main problem is ice crystal formation. When water freezes, it expands and forms crystals that can rupture cell membranes and destroy tissue structure. Even with cryoprotectant chemicals that reduce ice formation, damage occurs. Some researchers are exploring vitrification, a process that turns biological tissue into a glass-like solid without ice crystal formation. This has shown promise in laboratory settings, but scaling it up to whole human bodies and reliably reversing the process remains theoretical. Organizations like the Alcor Life Extension Foundation offer cryopreservation services, freezing people immediately after legal death in the hope that future technology will enable revival and medical repair. Whether this will ever be possible remains unknown. Even if we solve the technical problems of cryopreservation, there's another issue. Who maintains the ship during the journey? Who performs course corrections, monitors systems, and responds to unexpected problems? You would need either sophisticated artificial intelligence capable of operating autonomously for millennia, or a rotating crew that takes turns in suspended animation, with some members always awake to manage the vessel. Both approaches present their own challenges. The artificial intelligence route is particularly interesting and concerning. We're making rapid progress in machine learning and AI systems, but creating an intelligence capable of truly autonomous operation over geological timescales is another matter entirely. The AI would need to handle not just routine operations but unexpected emergencies, make complex decisions without human input, and maintain its core programming and mission objectives for millions of years without drift or corruption. This connects to debates happening right now in the AI research community. How do we ensure AI systems remain aligned with human values and goals? How do we prevent goal drift or unintended consequences? These questions become vastly more critical when we're talking about an AI that might be humanity's only representative in intergalactic space for longer than our species has existed. There's also the concept of digital consciousness or mind uploading. Some futurists and researchers like Ray Kurzweil and researchers at organizations like the Future of Humanity Institute have speculated about the possibility of mapping the complete structure of a human brain and recreating it in digital form. If consciousness could be transferred to a computer substrate, digital minds could potentially survive journeys of any length without the biological limitations of food, water, or air. They could be backed up, repaired, and would experience time in whatever manner their computational substrate allowed. This idea ventures into deeply philosophical territory. What is consciousness? Can it be separated from biological brains? Would a digital copy of your mind actually be you, or just a simulation that thinks it's you? These questions have occupied philosophers for decades, from Derek Parfit's work on personal identity to current debates in the philosophy of mind. We're nowhere near resolving them, and we're certainly nowhere near the technology to attempt mind uploading, if it's even possible in principle. But let's entertain the possibility for a moment. If digital consciousness were achievable, it could fundamentally transform the equation of leaving the Milky Way. Digital minds wouldn't experience time the same way biological entities do. They could potentially slow their subjective experience during the journey, making centuries pass like days, or even enter a state of suspended computation and reactivate upon arrival. The spacecraft could be far smaller and simpler without the need for life support, food production, or radiation shielding beyond protecting the computer hardware. Of course, this assumes the hardware could survive the journey. Cosmic radiation, micrometeorite impacts, mechanical failures over millions of years, these would still pose serious threats. You would likely need multiple redundant systems, self-repair capabilities, and robust error correction. Some concepts propose using DNA or quartz crystals as long-term data storage, as both have demonstrated remarkable stability over millions of years under the right conditions. Scientists have successfully stored digital information in DNA and retrieved it, and quartz disks have been proposed as archival storage that could last billions of years. Now I want to address something that often comes up in discussions of interstellar travel: exotic physics. Could there be loopholes in the laws of physics as we currently understand them? Could technologies like warp drives or wormholes make the journey feasible? The short answer is that we don't know, and the longer answer is fascinating but sobering. The concept of a warp drive gained scientific credibility in 1994 when physicist Miguel Alcubierre published a paper describing how, in principle, space-time itself could be warped to propel a spacecraft faster than light without violating relativity. The idea is that instead of moving through space, you compress space in front of the ship and expand it behind, essentially creating a bubble that surfs through space-time. The ship itself would remain stationary within its local space-time bubble, experiencing no acceleration or time dilation. Alcubierre's mathematics are valid within the framework of general relativity. Einstein's equations don't forbid such a configuration of space-time. The problem is what the equations require to make it work: exotic matter with negative energy density. This is matter that would have less than zero energy, which we've never observed and have no idea how to create, or even if it can exist in the quantities required. Theoretical calculations suggest you would need the mass-energy equivalent of Jupiter, or even more, worth of this exotic matter. Some researchers, like Harold White at NASA's Eagle Works laboratory, have explored whether modifications to the Alcubierre design might reduce these energy requirements. White proposed a modified geometry that, according to his calculations, might reduce the exotic matter requirement to something closer to the mass of a small spacecraft. But even these optimistic estimates remain purely theoretical, and the fundamental requirement for exotic matter hasn't been eliminated. There's also the causality problem. If you could travel faster than light, even using a warp drive trick, you run into the possibility of traveling backward in time, at least from certain reference frames. This creates the potential for grandfather paradoxes and violates our understanding of cause and effect. Some physicists argue that the universe must have some mechanism that prevents such violations, perhaps making warp drives impossible in practice, even if they're not strictly forbidden by the equations. Wormholes present a similar situation. These are theoretical tunnels through space-time that could connect distant locations, allowing instantaneous travel between them. Einstein and Nathan Rosen described these structures mathematically in 1935, and they're permitted by general relativity under certain conditions. The catch, again, is exotic matter. To keep a wormhole open and traversable, you would need exotic matter to counteract the natural tendency of the wormhole to collapse. You would also need to create or find the wormhole in the first place, and we have no observational evidence that natural wormholes exist. Kip Thorne, the Nobel Prize-winning physicist who served as scientific consultant for the film Interstellar, has done extensive work on the theoretical physics of wormholes. His research suggests that even if traversable wormholes could be created, they would likely be incredibly small, perhaps microscopic, and enlarging them to useful sizes would require technology and energy sources beyond anything we can currently conceive. The wormhole depicted in Interstellar, while based on real physics, represents an extreme best-case scenario that assumes multiple technological breakthroughs we have no path toward achieving. Here's the fundamental issue with all these exotic physics solutions. We're currently operating with physics that has been tested and verified across an enormous range of conditions, from the quantum scale to the cosmological scale. General relativity and quantum mechanics have been confirmed by countless experiments and observations. They make predictions that match reality with extraordinary precision. When we start invoking exotic matter, warp drives, or wormholes, We're not just talking about engineering challenges, we're talking about physics that may simply not be possible, regardless of how advanced our technology becomes. This doesn't mean we should stop exploring these ideas. Science advances by pushing boundaries and questioning assumptions. Quantum mechanics seemed absurd when it was first proposed, violating our intuitions about reality, yet it turned out to be correct. Dark matter and dark energy, which together make up 95% of the universe's total mass energy, were completely unexpected discoveries that forced us to revise our understanding of cosmology. Future discoveries could certainly reveal new physics that opens possibilities we can't currently imagine. But responsible science communication requires honesty about what we know, what we don't know, and what seems likely versus what's pure speculation. Right now, based on physics as we understand it, leaving the Milky Way appears to require either impossibly long journey times with conventional propulsion or technologies that may be fundamentally impossible. That might sound depressing, but I find it awe-inspiring in a different way. It reveals just how vast and magnificent the universe truly is. Think about what this means for our place in the cosmos. We are bound to our galaxy, perhaps permanently, by the sheer scale of space itself. The Milky Way is our cosmic home in a very real sense. Not just the planet we evolved on or the solar system we currently inhabit, but the entire galaxy containing hundreds of billions of stars, each potentially hosting worlds of their own. This is our domain, our realm to explore and understand. And exploring our galaxy alone would be an achievement beyond imagination. If we could develop the ability to travel between stars, even if we never leave the Milky Way, we would have access to 100 billion stellar systems. That's 100 billion potential destinations, each unique, each offering new worlds and phenomena to study. We could spend millions of years just exploring our immediate galactic neighborhood and barely scratch the surface. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized our understanding of planetary systems by discovering thousands of exoplanets orbiting other stars. Its successor, the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, continues this work. These missions have revealed that planets are incredibly common. Nearly every star has at least one planet, and many have multiple worlds orbiting them. Some of these planets are rocky and located in their star's habitable zone, where liquid water could exist on the surface. The James Webb Space Telescope, humanity's most powerful space observatory, launched on Christmas Day 2021, is now studying the atmospheres of some of these exoplanets, looking for biosignatures, chemical signs that might indicate the presence of life. Early results have detected water vapor, carbon dioxide, and other molecules in distant planetary atmospheres. We're living in an era where we can actually characterize worlds orbiting other stars, measuring their temperatures, compositions, and atmospheric properties. These discoveries transform our understanding of the galaxy from an abstract concept into a concrete reality filled with actual places we could theoretically visit. Each of those exoplanets is a real world with its own geology, weather patterns, and possibly even biology. The TRAPPIST-1 system, discovered in 2017 and located just 39 light-years away, contains 7, roughly, Earth-sized planets orbiting an ultra-cool red dwarf star. 3 of these planets orbit within the habitable zone. What might we find if we could send a probe there? Proxima Centauri b, orbiting the nearest star to our Sun at a distance of just over 4 light-years, is another tantalizing target. Discovered in 2016, this planet orbits within its star's habitable zone and might have conditions suitable for liquid water. The Breakthrough Starshot initiative, announced that same year by physicist Stephen Hawking and entrepreneur Yuri Milner, proposes sending tiny, light-sail-equipped probes to the Alpha Centauri system at 20% the speed of light, reaching the system in roughly 20 years after launch. Breakthrough Starshot envisions using powerful ground-based lasers to push small, gram-scale spacecraft equipped with light sails up to relativistic speeds. The concept is technically challenging, but doesn't require any new physics. Light carries momentum, and a sail can capture that momentum for propulsion. By concentrating enormous laser power on tiny, lightweight probes, you could achieve accelerations impossible with conventional rockets. The probes would zip past their target, collecting data during a brief flyby and transmitting it back to Earth. This represents one of the few realistic near-term pathways to interstellar exploration. Not crude missions, not colony ships, but tiny robotic scouts that could reach nearby star systems within a human lifetime. Even this requires tremendous technological development. The lasers would need to output approximately 100 gigawatts of power, comparable to the output of 100 nuclear power plants, focused with incredible precision on a sail just meters across. The spacecraft would need to survive the acceleration, navigate interstellar space, and maintain communication across light years. But it's achievable in principle, and serious engineering studies are underway. If successful, Breakthrough Starshot could return the first close-up images and data from an exoplanet in the latter half of this century. That would be a historic achievement, extending humanity's reach beyond the solar system for the first time. Yet even at 20% light speed, exploring just our local stellar neighborhood would take centuries. Reaching the galactic edge would still require millions of years. This brings us back to the central tension of our topic. The galaxy is both our cosmic home and our prison. We can study it from afar with ever-improving telescopes. We can potentially explore nearby stars with robotic probes and, perhaps someday, with crewed missions using technologies we're just beginning to develop. But leaving the galaxy entirely appears to be beyond our reach, possibly forever, unless physics has surprises in store that we haven't discovered yet. Some people find this limiting and disappointing. I understand that reaction. We're a species that loves to explore, to push boundaries, to see what's over the next horizon. The idea that there are absolute limits to where we can go can feel constraining. But I'd like to offer a different perspective. The fact that we're confined to our galaxy doesn't diminish the grandeur of the universe. If anything, it enhances it. Consider the alternative. If travel between galaxies were easy, if we could zip across the universe at will, the cosmos would somehow feel smaller, more manageable, less awe-inspiring. The fact that distances are so vast that they fundamentally limit what's accessible to us speaks to the true scale of reality. We are tiny beings on a small planet orbiting an ordinary star in a galaxy of hundreds of billions of stars, which is itself one of hundreds of billions or even trillions of galaxies in the observable universe. The observable universe, that's another crucial concept to address. When we talk about the universe, we often mean different things. There's the observable universe, which is the spherical region around us from which light has had time to reach us since the Big Bang. That's approximately 93 billion light-years in diameter, accounting for the expansion of space during the time light has been traveling. Beyond that is presumably more universe, possibly infinite, but we can never observe it directly because the light hasn't had time to reach us yet. The Milky Way, vast as it is, spans only about 100,000 light-years across its disk. The observable universe is almost 1,000,000 times wider. Our galaxy represents roughly 1/10,000,000th of the observable universe's volume. When you look at it that way, even if we could explore our entire galaxy, we would still be confined to an infinitesimally tiny corner of existence. The universe is constructed on scales that dwarf our intuition and exceed our ability to fully comprehend. This is where I think the real beauty and meaning emerges. We're part of something unimaginably vast, something that extends far beyond what we can ever hope to explore or even observe. Our significance doesn't come from being big or being able to travel everywhere. It comes from being able to understand, to ask questions, to map the cosmos with mathematics and observation, to figure out our place in this grand structure. You are made of atoms forged in the cores of ancient stars. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all of it was created in stellar furnaces billions of years ago. Those stars lived their lives, exhausted their fuel, and died in spectacular supernova explosions that scattered their enriched material across space. That material eventually collapsed into new solar systems, including ours, and eventually became part of you. When you look up at the night sky, you're looking at your ancestors in a very literal sense. You're also looking backward in time. The light from distant stars left those stars years, decades, centuries, or millennia ago. When you see the Andromeda Galaxy with binoculars or a small telescope, you're seeing light that left that galaxy 2.5 million years ago, before modern humans existed. You're literally seeing into the past. This temporal component of cosmic distances adds another layer to our question about leaving the Milky Way. Even if we could send a signal to someone beyond the galaxy, and even if they could respond instantly, which would violate the speed of light limit, we wouldn't receive their response for 1 million years. Communication across intergalactic distances isn't just impractical, it's essentially impossible in any meaningful sense. This might partially explain the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If the universe is so vast and so old, and if planets are common, and if life can arise on planets, then why haven't we detected any signs of extraterrestrial civilizations? The paradox has generated dozens of proposed solutions, from the possibility that we're alone, to the idea that civilizations inevitably destroy themselves, to the concept that advanced beings are deliberately avoiding contact. But one often overlooked factor is simply the vastness of space and time. Even if intelligent civilizations are relatively common on a galactic scale, the distances between them might be so enormous that contact is effectively impossible. If every civilization is confined to its own galaxy by the same physical limits we face, then the universe might be teeming with life, all isolated from each other by gulfs of space too wide to cross. This isolation could be fundamental to the structure of the universe itself. Some cosmologists have speculated that galaxies might function as isolated island universes, a term actually used by philosophers and astronomers in the 18th and 19th centuries, before we understood what galaxies were. Each galaxy would develop its own biological and technological history, completely independent of all others, forever separated by distances that no amount of advancement could overcome. There's something both lonely and comforting about this idea. Lonely because it means we might never meet our cosmic neighbors, never share knowledge with civilizations that have solved problems we're struggling with, never participate in some grand galactic community. But comforting because it means that whatever happens in our galaxy is up to us. There's no external threat coming from beyond, no alien civilization that will conquer or judge us. Our future is genuinely open and in our own hands. It also suggests that if we want to find life, we should focus on our own galaxy. The search for extraterrestrial intelligence, or SETI, has been scanning the skies for radio signals from alien civilization since the 1960s. Most SETI programs focus on nearby stars within our galaxy, which makes sense given the distances involved. Even signals from the far side of the Milky Way would take tens of thousands of years to reach us, which is challenging, but not impossible. Signals from beyond the galaxy would take millions of years and would be so faint as to be essentially undetectable. Recent years have seen renewed interest and funding for SETI research. Breakthrough. Listen, another initiative funded by Yuri Milner, is conducting the most comprehensive search ever undertaken, surveying 1 million nearby stars and 100 nearby galaxies. So far, no confirmed detections, but the search continues. Even a null result tells us something important about the prevalence and behavior of technological civilizations. Meanwhile, astrobiology, the study of life in the universe, is focusing increasingly on finding microbial life within our own solar system. Mars, with evidence of ancient rivers and lakes, might have hosted life billions of years ago and possibly still does in subsurface environments. Europa and Enceladus, moons of Jupiter and Saturn respectively, have subsurface oceans beneath icy crusts, heated by tidal forces from their giant parent planets. These oceans could potentially harbor life. NASA's Europa Clipper mission, launched in October 2024, will arrive at Jupiter in 2030 to conduct detailed studies of Europa, including measuring the thickness of the ice, characterizing the ocean beneath, and analyzing plumes of water vapor that appear to erupt from the surface. If we found life on Europa, even simple microbial life, it would be one of the most significant discoveries in human history. It would tell us that life can arise independently in multiple locations, that Earth isn't unique, and that the universe might indeed be full of life. Finding life on another world in our solar system, or detecting biosignatures in the atmosphere of a nearby exoplanet, would transform our perspective. It would change the question from, are we alone, to how common is life? And if microbial life is common, then complex life might also be common, and intelligent life might be rarer but still present in significant numbers across the galaxy. This brings me to an important point about the search for life and the exploration of the cosmos. We often think about space exploration in terms of human missions, astronauts planting flags, colonies on other worlds, but the vast majority of exploration, both now and in the foreseeable future, will be done by robots and remote sensing. We've explored Mars extensively using rovers like Curiosity and Perseverance. We've studied Jupiter's moons, Saturn's rings, and Titan's methane seas using orbiters and probes. We've even landed on comets and asteroids. These robotic missions extend our senses and presence to places no human could currently survive. They're extraordinarily cost-effective compared to crewed missions, and they don't risk human lives. The entire Curiosity rover mission to Mars cost about $2.5 billion, roughly the cost of a single large aircraft carrier, and has been operating for over a decade, making groundbreaking discoveries. A crewed Mars mission would cost hundreds of billions and face enormous life support challenges. I'm not arguing against human spaceflight. There's something irreplaceable about human intelligence, adaptability, and the symbolic importance of people physically traveling to new worlds. But our exploration of the galaxy will necessarily involve a partnership between humans and machines, with robots doing the vast majority of the actual travel, while humans remain in locations where they can survive, using telescopes, probes, and eventually perhaps mind-machine interfaces to experience distant locations. This hybrid approach might be how any intelligent species explores its galaxy. You develop the technology to survive in space habitats, colonize nearby worlds that can be terraformed or lived on with appropriate technology, send robotic probes to study more distant stars, and use advanced telescopes to observe the broader universe. You map your galaxy over thousands or millions of years, gradually expanding your direct presence, while using technology to extend your awareness far beyond where you can physically go. If we follow this path, what would humanity's future in the galaxy look like? Let's engage in some informed speculation, grounded in physics and biology, but imaginative about timescales and persistence. Suppose humanity survives the various challenges we currently face: climate change, nuclear weapons, pandemics, artificial intelligence risks, and resource depletion, and successfully becomes a spacefaring species. What might the next million years look like? Initially, we would probably focus on our solar system. Establishing permanent settlements on the Moon and Mars within this century is plausible with sustained effort and funding. These wouldn't be small scientific outposts like the International Space Station, but actual communities of hundreds or thousands of people with agriculture, industry, and eventually self-sustaining economies. Children would be born who had never seen Earth. Beyond Mars, we might develop the ability to live in space habitats, rotating cylinders or tori that use centripetal force to simulate gravity. The physicist Gerard O'Neill designed detailed concepts for such habitats in the 1970s, showing how they could support populations of thousands or even millions in cylinder-shaped structures positioned at stable points in space. These habitats could be built using materials from asteroids, which contain vast quantities of metals, water ice, and other resources. The asteroid belt, located between Mars and Jupiter, contains millions of asteroids ranging from tiny rocks to dwarf planets hundreds of kilometers across. The total mass of the asteroid belt is significant, enough to build countless space habitats if we develop the mining and construction technology. Some estimates suggest the material in the asteroid belt could support a total human population in space habitats numbering in the trillions, far exceeding Earth's current population. Mining asteroids and building space habitats would take centuries, but it's achievable with foreseeable technology. Companies are already working on asteroid mining concepts, though economic viability remains uncertain. Luxembourg and the United States have both passed legislation recognizing property rights for resources extracted from asteroids, creating a legal framework for what was previously purely theoretical. Once we've thoroughly settled our solar system, the next logical step would be nearby star systems. As I mentioned earlier, Proxima Centauri at 4.2 light-years is the closest target. At 10% the speed of light, which would require tremendous energy but no new physics, a journey there would take 42 years. That's within a human lifetime. Someone could board a ship as a young adult and arrive at Proxima Centauri in late middle age. The engineering challenges would be immense. The spacecraft would need to be self-contained for decades, with closed-loop life support, reliable propulsion, radiation shielding, and the ability to decelerate at the destination. That last point is often overlooked. It's one thing to accelerate a spacecraft to high speed using years of constant thrust or even a brief but powerful boost. It's another thing entirely to slow down when you arrive. You would need either to carry enough fuel to decelerate, which massively increases the mass of your ship, or use some form of magnetic sail that could interact with the destination star's solar wind, or deploy a forward-facing light sail that could be illuminated by powerful lasers at the destination star. Each approach has drawbacks. Carrying deceleration fuel makes the ship heavier, requiring more fuel to accelerate it in the first place. This is the tyranny of the rocket equation, exponentially increasing fuel requirements. Using magnetic sails or forward light sails requires technology at the destination, which wouldn't exist for the first mission to a star system. The first interstellar voyagers might have to accept a flyby mission rather than entering orbit, collecting data during a brief passage and transmitting it back to Earth. But let's imagine we solve these problems. Over centuries, we send missions to dozens, then hundreds of nearby stars. Some missions fail due to equipment malfunction, navigation errors, or unforeseen hazards. Others succeed, establishing outposts around promising star systems. Each outpost becomes a stepping stone, a base from which to launch missions to other nearby stars. Gradually, a network of human settlements spreads through the Orion arm of the galaxy, the spiral arm where our solar system is located. This expansion wouldn't be rapid or coordinated. Each settlement would be separated from Earth by years or decades of communication delay. A message from a colony 10 light-years away would take 10 years to reach Earth, and the response would take another 10 years to arrive. Real-time conversation would be impossible. Each community would necessarily develop significant independence, making decisions without waiting for input from Earth. Over thousands of years, these communities would diverge culturally and possibly biologically. Humans living on a low-gravity world might evolve taller, thinner bodies. Those on high-gravity worlds might become shorter and more robust. Communities living in isolated space habitats might develop unique cultural practices, languages, and social structures. The branching of humanity into distinct populations has happened repeatedly in our history, from the peopling of different continents to the development of isolated island cultures. It would happen again on a galactic scale. Eventually, these distant communities might have more in common with their nearby stellar neighbors than with Earth. Someone living around Tau Ceti, 11.9 light-years from Earth, would find it easier to communicate and trade with settlements around Epsilon Eridani, 9.4 light-years from Tau Ceti, than with Earth. which would be nearly 12 light-years distant. Local networks would form, creating regions of human civilization connected by trade, communication, and cultural exchange, while connections to Earth faded into historical memory. This is actually consistent with how civilizations have developed on Earth. Ancient Polynesian navigators settled islands across the Pacific over thousands of years, creating networks of related but distinct cultures. Some islands maintained contact with nearby neighbors while losing connection to more distant origin points. Something similar would happen across interstellar distances, except the isolation would be more severe and permanent due to the light-speed communication limit. Now let's think about timescales. If we began serious interstellar colonization in the 23rd century, a wildly optimistic timeline, and if each new settlement sent out its own missions to nearby stars every few centuries, how long would it take to spread throughout the galaxy? Various models have been proposed by scientists studying this question, and the answer depends heavily on your assumptions about travel speed and how long settlements wait before sending out new missions. One influential study by physicist and author Geoffrey Landis calculated that even at very modest speeds, well below 1% the speed of light, a colonizing civilization could spread throughout the entire galaxy in approximately 50 million years. Other models with more optimistic assumptions about speed and colonization rates suggest timelines as short as 5 to 10 million years. These are enormous spans of time, comparable to the period since the common ancestor of humans and chimpanzees, but they're brief compared to the galaxy's age of over 13 billion years. This creates an interesting puzzle related to the Fermi paradox I mentioned earlier. If interstellar colonization is possible, even if slow and difficult, and if the galaxy is billions of years old, then even if intelligent life is rare, any species that arose even tens of millions of years before us should have had time to spread throughout the galaxy. The fact that we don't see evidence of such colonization, no artificial structures, no radio signals, no signs of industrial activity on a massive scale, suggests either that intelligent life is extraordinarily rare or that something prevents civilizations from engaging in this kind of expansion. Possible explanations are numerous. Perhaps intelligent life is so rare that we're the first in our galaxy or among the first. Perhaps civilizations typically destroy themselves before becoming interstellar. Perhaps they choose not to expand, finding satisfaction in developing their home systems rather than spreading outward. Perhaps they do expand, but in ways we wouldn't recognize, using technology or methods so advanced they're invisible to us. Perhaps there's a fundamental barrier we haven't encountered yet that makes interstellar civilization impossible in practice. This is all deeply uncertain and speculative. What we can say with more confidence is that if humanity does spread through the galaxy over millions of years, we would still be confined to the Milky Way by the same physics that makes it difficult for us to leave now. Even a civilization that had colonized thousands of star systems and commanded energy on stellar scales would face the same fundamental problem. Intergalactic distances are simply too vast. In fact, the problem gets worse over time due to cosmic expansion. The space between galaxies is expanding, driven by dark energy, the mysterious force that's accelerating the universe's expansion. Galaxies that are currently 500,000 light-years away will be farther in the future, and the rate of expansion is increasing. Eventually, billions of years from now, galaxies beyond our local group will recede so rapidly that light from them will never reach us. They will pass beyond what's called the cosmic event horizon. This means the universe is actually becoming less accessible over time, not more. The long-term future sees galaxies becoming isolated island universes, permanently separated from each other, unable to communicate or interact. Our local group, consisting of the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies, will eventually merge into a single giant elliptical galaxy, while all other galaxies disappear from view as they recede beyond the cosmic horizon. This cosmological perspective is humbling and profound. Not only are we likely confined to our galaxy in any practical sense, but the universe itself is structured in a way that creates fundamental boundaries to what can ever be explored or observed. Even hypothetical super-advanced civilizations with technology indistinguishable from magic would face these same limits. The laws of physics aren't just suggestions. They're constraints that apply to everyone, everywhere, regardless of technological sophistication. There's a certain democracy to this. A civilization 1 billion years more advanced than us would still be unable to casually hop between galaxies. They would still face the same speed of light limit, the same vast distances, the same expanding space pushing galaxies apart. Whatever they achieved would be achieved within the same rules that govern our universe. This means our limitations aren't a reflection of our primitiveness, but rather a reflection of reality itself. That said, we shouldn't underestimate what could be accomplished within these constraints. The Milky Way contains an estimated 100 to 400 billion stars, depending on which measurements you trust. Current research suggests the higher end of that range is more accurate, with perhaps 400 billion stars in our galaxy. If even a small fraction of those stars have planets in their habitable zones, we're talking about billions of potentially habitable worlds just in our galaxy. The Kepler mission's data suggests that roughly 20 to 50% of stars have planets in or near their habitable zones, though this varies significantly depending on the type of star. If we take a conservative estimate and say that 1% of stars in the Milky Way have potentially habitable planets, that's 4 billion worlds. Even if only 1% of those actually develop conditions suitable for life as we know it, that's still 40 million planets. The numbers are staggering. Of course, habitable is a complex concept. We tend to think in terms of Earth-like worlds with liquid water, oxygen atmospheres, and temperate climates. But life might thrive in environments we consider hostile. Jupiter's moon Europa and Saturn's moon Enceladus have subsurface oceans that could potentially harbor life, despite surface temperatures hundreds of degrees below freezing. Titan, Saturn's largest moon, has liquid methane lakes and a thick nitrogen atmosphere. Some scientists speculate about exotic biochemistries that could function in liquid methane instead of water. If life can adapt to such diverse conditions, then the number of inhabited worlds in the galaxy might be much higher than we currently estimate. And if life is common, then the Milky Way might be teeming with biology, from simple microbes to complex ecosystems and possibly even other technological civilizations. All of this would be accessible, at least in principle, to a sufficiently advanced and patient spacefaring species like we might become. Imagine a future 1 million years from now where humanity, or whatever we've evolved into, has established a presence around thousands of star systems. We've discovered hundreds of worlds with native life, from bacterial mats to complex ecologies. We've made contact with a handful of other technological species, exchanging information across light-year distances at the speed of laser or radio transmissions. We've built structures on scales that would seem godlike to our contemporary selves. Dyson swarms capturing the energy of entire stars, space habitats housing trillions, computational systems with processing power exceeding all human brains, combined by factors of billions. Even with all this advancement, leaving the galaxy would remain essentially impossible. The distances would still be too great, the energy requirements still too enormous, the journey times still too long. But would it matter? Would a civilization with access to thousands of star systems, billions of habitable worlds within reach over millennia, and discoveries enough to occupy scientific attention for millions of years, would such a civilization feel limited by being confined to one galaxy? Perhaps not. Perhaps the desire to leave the galaxy is actually a reflection of our current limitations, not a fundamental drive. When you're confined to one planet, you dream of reaching the stars. When you've reached nearby stars, you dream of exploring the galaxy. When you've explored much of your galaxy, perhaps you focus on understanding it deeply rather than leaving it. The shift from extensive exploration to intensive study might be a natural progression for mature civilizations. This raises philosophical questions about the nature of progress and exploration. We tend to think of advancement as expansion, as going farther and faster, conquering new territories and pushing boundaries. But another form of advancement is deepening understanding, learning more about the places you already have access to, refining your knowledge and perception. You could spend 1,000,000 years studying a single complex ecosystem and still discover new things. You could study a single star system in complete detail and occupy scientific careers for generations. The universe isn't just large in space, it's also deep in complexity. Every level of organization, from subatomic particles to galactic superclusters, contains structures and phenomena that we've barely begun to understand. We don't fully comprehend how proteins fold, how consciousness arises from neural activity, how ecosystems maintain stability, or how galaxies form their spiral arms. These are problems accessible to us right now, not requiring interstellar travel, yet they remain partially or largely unsolved. A civilization that devoted its energy to understanding rather than just exploring might develop in profoundly different ways. Instead of spreading thinly across thousands of stars, they might establish a smaller number of settlements, but develop extraordinary depth of knowledge about their local environment. They might create art, philosophy, and science of incredible sophistication, building on millions of years of accumulated wisdom. This isn't to say exploration and expansion aren't valuable. They clearly are, and they've driven much of human progress. But it's worth considering that the inability to leave our galaxy might not be the limitation it initially appears. It might simply be reality telling us to look inward as well as outward, to study deeply as well as broadly, to appreciate the infinite complexity of what we can access rather than lamenting what we cannot. There's also the time dimension to consider. I've been talking about spatial distances, but temporal spans are equally important. The universe is approximately 13.8 billion years old. The Sun and Earth formed about 4.6 billion years ago. Complex life on Earth emerged relatively recently in geological terms, with the Cambrian explosion of animal diversity occurring about 540 million years ago. Humans have existed for perhaps 300,000 years. Technological civilization is mere thousands of years old. We're extraordinarily young as both a species and a civilization. The universe has existed for more than 40,000 times longer than our species. If we manage to avoid extinction and continue developing, we could potentially exist for millions or even billions of years into the future. Our current perspective, shaped by the concerns and capabilities of the early 21st century, might be as limited and parochial as a medieval peasant's view of global politics. In 1,000,000 years, if we still exist, what will our descendants think about the question of leaving the galaxy? Will they even frame it in the same terms? They might have discovered new physics that reveals possibilities we can't currently imagine. Or they might have concluded that galactic confinement is indeed permanent and restructured their civilization and aspirations accordingly. Or they might not think in terms of exploration and expansion at all, having developed motivations and goals we can't currently conceive. This uncertainty about the future is both unsettling and liberating. We can't predict what will happen over such vast timescales, too many variables, too many potential discoveries, too many possible paths. But that openness means the future is genuinely unwritten. What we do now, the choices we make as a civilization, the values we preserve or abandon, the technologies we develop or suppress, all of this matters. We're not just passengers watching predetermined events unfold. We're active participants shaping what comes next. So, can we leave the Milky Way? The honest answer, based on our current understanding of physics, is almost certainly no, not in any meaningful sense. The distances are too vast, the energy requirements too extreme, the journey times too long. Even with significant technological advancement, intergalactic travel appears to be beyond the realm of the possible, barring discoveries that would revolutionize our understanding of space-time itself. But this limitation doesn't diminish our potential or our significance. The Milky Way contains hundreds of billions of stars and potentially billions of habitable worlds. It's a realm vast enough to occupy explorers for millions of years, diverse enough to host countless forms of life, and complex enough to challenge scientific understanding for eons to come. Being confined to our galaxy is like being confined to an ocean containing billions of islands, each with its own ecosystems, resources, and mysteries. Our significance doesn't come from being able to go everywhere or do everything. It comes from our ability to understand, to ask questions about the cosmos and derive answers through observation and reasoning. We're a way for the universe to know itself, as Carl Sagan memorably put it. We're matter that has become conscious, organized into structures complex enough to contemplate our own existence and our place in the grand scheme of things. The atoms in your body were forged in stellar furnaces. The elements that make you possible were created in the nuclear fusion cores of stars that lived and died before our sun was born. You are literally made of star stuff, chemically connected to the entire cosmos. When you look up at the night sky, you're not just observing distant objects, you're seeing your origins, your context, your cosmic family. And increasingly, we're able to not just observe, but understand. We can explain how stars form from collapsing clouds of gas and dust. We can predict their life cycles based on their mass. We can calculate the structure of galaxies, trace the evolution of the universe back to its first moments, and project forward billions of years to predict its ultimate fate. This understanding is itself a kind of transcendence, a way of mentally traveling to places our bodies can never reach. Perhaps that's the real answer to our question. Physically leaving the Milky Way is likely impossible, but intellectually we've already gone far beyond it. We've mapped the cosmic microwave background radiation from the edge of the observable universe. We've observed galaxies forming in the early universe, seen black holes merging billions of light years away, and traced the large-scale structure of cosmic web that spans hundreds of millions of light years. Our minds and our instruments can reach where our bodies cannot. This capacity for understanding might be more valuable and more significant than physical exploration. A civilization that deeply understands its universe, even if confined to one galaxy within it, has achieved something remarkable. It has overcome the limitations of local perspective and grasped the larger patterns and principles that govern all of existence. So, no, we probably can't leave the Milky Way, but we can understand it, explore it, and potentially spread throughout it over timescales we can barely imagine. We can discover whether life exists elsewhere in our galaxy, learn from other biospheres, and possibly other civilizations, and create a future that extends millions of years into time and thousands of light years through space. That's not a limitation, that's an opportunity of cosmic proportions. The Milky Way is our home, our inheritance, and our frontier. Within it lies more than enough to inspire wonder, challenge our understanding, and occupy our species for as long as we exist. The fact that we're unlikely to leave it doesn't make us prisoners. It makes us residents of a realm so vast and magnificent that exploring and understanding it could occupy humanity for the entire remaining lifespan of the universe. In the end, maybe the question isn't whether we can leave the Milky Way, but whether we can become worthy stewards and explorers of the galaxy we already have. That's a challenge that will require wisdom, cooperation, technological advancement, and the ability to think on timescales far beyond our individual lives. It's a challenge worthy of a species that dreams of touching the stars. The universe has given us a galaxy containing hundreds of billions of suns, an incomprehensible abundance of worlds to discover, and possibly life to encounter. That's not confinement, that's a gift beyond measure. Our task is to use it wisely, explore it thoroughly, and perhaps millions of years from now, to have become something worthy of such an extraordinary cosmic inheritance. If you made this far, please subscribe to the channel and give a like. And if this exploration of cosmic scales has left you contemplating our place in the universe, I invite you to watch my video called The Terrifying Truth About Our Size in the Universe, where I dive even deeper into the mind-bending reality of just how small we truly are in the grand cosmic scheme. The video is on the screen. See you there.